Hey, can you hear me?
Yeah, I can. Yeah.
Oh, oh, hey.
And you can hear me?
Yeah, I can hear you just fine.
Awesome. Yeah.
All right.
Cool.
How have you been?
Oh, excellent. So much fun stuff to work on.
Like what? I know you specialize in computational neuroscience. Like what specifically in that?
Well, I used to work on computational neuroscience, and then I slipped over into philosophy and thinking about human enhancement, ethics, global risks, and grand futures. And over the past few weeks, I've been finishing up on an old big project. So it's a lot of papers I'm dusting off and trying to send out. So one of them is about, is there a risk that the particle accelerators could turn Earth into dark matter? And the interesting thing is, no, I don't believe there is that risk. And in calming the friends who came up with that concern, I realized, I actually need to do a bit of legwork to make a good argument that can convince him in a scientific way. And once that's done, he's going to come up with another crazy scenario about how maybe particle accelerator could melt down Earth. So is there some more generic way of reasoning about these very weird risks at the edge of physical possibility? So that's one of the papers I've been working on. Another one is about why a particular method of forecasting the future never works, or very rarely works.
That's cool.
Yeah,
Also, how can particle accelerators? How can they produce dark matter anyway? Because I thought it only exists around galaxies.
well, think about what a particle accelerator does. You take two particles, accelerate them to a very, very high velocity. Uh, at this point, Einstein and relativity theory steps in and says, yeah, that energy you put into them, that's actually equivalent to mass. So when they smash into each other, there is a lot of energy that could be turning into mass of particles. So you get an entire shower of little particles. Some of them might have been parts of the original particles. Some of them are just energy turning into elementary particles. And then physicists are happily measuring this and trying to figure out if there are new kinds of particles or interactions going on. So if there is some interaction between normal particles that can produce dark matter particles, maybe we should be able to see that in particle accelerator. This was one of the things everybody was saying. This is why we want to build the Large Hadron Collider. We really, really want to check what dark matter is made out of. Of course, we also want to find by Higgs boson and a lot of other things. But finding the dark matter particles would be awesome, assuming dark matter actually is consisting of little elementary particles. The problem is, of course, you can't really detect them. So if you generate them, you would just see some energy mysteriously disappearing. So it's a slightly tricky thing to measure, but there are precedents. This is how we found the neutrino back in the 1930s. Back then, people were looking at beta decay in atomic nuclei, and they noticed that the energy distribution didn't make sense unless some of the energy went off with a particle that you couldn't detect. And for a long while, people felt, oh, this is kind of yucky. This is not good science, assuming an undetectable particle. But everybody were really happy, of course, once they actually found the neutrino. Okay, now our theory is working really well. Similarly, we might say the same thing about making dark matter particle in a particle accelerator. Yeah, it's going to take a bit of tricky testing to prove that, yeah, the energy went away in a particle we don't know and recognize. After all, it could be that you're just making a lot of neutrinos or something else that's hard to detect. The problem is, however, that the Large Hadron Collider has not seen a faintest trace of this kind of interaction. There is no good evidence at all that you can make dark matter particles in that accelerator, which is a kind of embarrassing thing.
Yeah, it is because many physicists were hoping that they would, well, not just discover just dark matter. Well, not discover, it's already discovered, assuming it exists, but figure out what it is in dark energy and the hierarchy problem and lots of other
Yeah.
mysteries. But of course, the main problem might be they just need to produce a higher particle energy. Or maybe dark matter interacts even more weakly than they think. Is that possible?
Totally. That's a problem. You could imagine dark matter that doesn't interact at all with the normal sector of physics we see. So you can't make it unless you have a new Big Bang. That's entirely allowed theoretically. It's just that it's a super awkward thing. So you mentioned the hierarchy problem. So this is the issue of what gives the different mass scales for different particles. We have good reason to think that the different neutrinos, for example, have slightly different masses. Even though we don't know exactly what the mass is, it's possible to detect that there must be a difference between them. And similarly, the up and down quarks that make up of most of the baryonic matter we see around us, very much lighter than the charm and strange quarks, which are in turn way lighter than the top and bottom quarks. So why that difference shows up is kind of a theoretically profound question, and figuring it out better would be great. The big problem with the Large Hadron Collider has been that it found exactly the stuff we expected to find and nothing else. And that's, of course, the worst situation ever for physics, because if you don't have any little string to pull on, you're not going to be able to find the new stuff. We know that our understanding of the cosmos is not really complete. So this is why the recent results from Fermilab, the G-2 collaboration, were so exciting. Oh, look, here is something the standard model gets wrong. It's a very small error, but it seems to be clear that there is a problem.
Yeah, I would like to know more about particle acceleration physics. Excuse me. Specifically, why is the hierarchy problem? Why is that even a problem? Like, do they believe that there must be some underlying mechanism for the different strengths and ranges of the forces, or they just don't know yet? Like how the strong force is really short ranged, mediated by gluons. Do they think it's by chance, or maybe there's some other particle causing it, or what's that about?
So the deep question is, why is the standard model like it is? So once upon a time, we had a whole bunch of different physical forces, and gradually they started to unify. First, electricity and magnetism. That was kind of a ground unification of the 19th century. Whoa, they can be described by just four really cool equations, and you can make a lot of predictions. That's great. And then there was a lot of other stuff going on. And then we found that, okay, there is, of course, gravitation, and we have strong and weak nuclear force. And then you can find that, oh, we can combine the electromagnetism and the weak nuclear force and get a theory, electroweak theory, that works really well. And then we got the standard model in about 1968, people formulated it. And in the years since, it has worked out really well. Now, when you think about how particle physicists like to think about physics, it's all about symmetry. You're thinking about the fields making up the universe as having various symmetry properties between each other. Magnetism and electricity, for example, have this nice duality between each other. You can kind of flip between them in some mathematical sense, even though they behave very differently in everyday life. They are actually deep down two sides of the same coin. And it turns out that these symmetries are super useful. So Emmy Noether, she proved one of the most important theorems ever in the early part of the 20th century. That if you have a continuous symmetry for the kind of physics you're describing, you get a conserved quantity. So the fact that physics is unchanged depending on the time of day, that gives you actually energy conservation. This is actually how you can define energy. Energy is that which is conserved because of time translation invariance. And space in the translation invariance, physics is the same in a lab wherever it is in the world. Well, that actually gives you conservation of momentum. And rotation, well, it doesn't matter if your lab is pointing south or east. Yep, now you get conservation of angular momentum. So this is beautiful. It's very good math, assuming, of course, physics actually follows the formalism Noether assumed, which is an important if not necessarily true. But ever since, physicists have found that if you understand the symmetry, you get these conserved quantities, you get elementary particles corresponding to the symmetry. So people found early on that protons and neutrons are almost the same thing, except of course protons has a positive charge and neutrons are neutral. But in an atomic nucleus, the forces behave as if they were just the same thing. So it seems like you could actually talk about nucleons, just this mixture of proton and neutron, and say that, yeah, that symmetry is kind of unbroken under the strong nuclear force. So gradually we got the standard model, which is expressed as a lot of symmetries working together. The problem here is the standard model is beautiful in one way, but then you find that it has about 20 parameters describing the strength of different things. And these are the annoying ones because they're not beautiful at all. There is nothing in the theory that tells you what values they should have. And some of them have really weird values. Some of them are angles, and why should something be something like 13.5 degrees? That's kind of weird. And some of them are the masses of elementary particles. Yeah, you can explain some of them by how strongly they interact with the Higgs boson, but then you have a new problem. Okay, what determines that strength of interaction? And this could be, of course, that, well, maybe it's just random. And in universes where these random values have the wrong values, you can't get matter and biology and observers doing physics. So maybe it's just no truth to it. It's just this is a consistent set. But some of them might also be due to deeper symmetries or deeper things. And that's, of course, what everybody were hoping for. In particular, people were hoping to find supersymmetry. But all the normal stuff, unfortunately, it seems to be almost dead in the water these days, because if there was some kind of supersymmetry, it should have been found in the particle accelerators by now.
Hold on a second. Microphone's messing up. Hey, can you hear me?
Yep, no problem.
Okay. Yeah, yeah, because you mentioned the LHC creating dark matter particles. People were always afraid that the LHC would create a black hole, or rather a micro black hole. Is that actually possible?
Well, that's another good question. So when physicists started to think about unifying the different theories, one of the fundamental problems was gravity is not like the other forces in nature. General relativity has this beautiful way of describing gravity as curvature of space-time. All the other theories are about exchanging particles. And yeah, you can start hand waving and saying maybe they're graviton particles, but basically the kind of math that you get in quantum field theory is really incompatible with general relativity. And people have been trying to figure out clever ways of unifying it. But if you excuse me 1 moment, I can't, I can't do anything about that phone. We just need to wait until my mother picks it up. Sorry for that.
Oh, that's interesting. Uh,
Yeah,
yeah.
yeah. Well,
Why?
oh,
So about general relativity and black holes, I told you a while. I asked you a while back about the conservation of quantum numbers, right? And how if black
yeah.
holes really only have mass, spin, and angular momentum, doesn't that mean they destroy the other conserved quantities? Like I think one number is color charge or something, and another is baryon number. Doesn't that mean those get destroyed?
Yeah. So you can totally destroy baryon number by taking a black hole and feeding it either protons or sorry.
Okay. Okay.
The problem is okay, now it seems to have gone away. Okay, let's hope. Yeah. So if you have a black hole and feed it protons or antiprotons, there is no difference. It just grows the same amount. So it seems like it doesn't respect the proton or baryon number. And this goes, of course, for a lot of other properties. So clearly, the general relativity doesn't play nice with the standard model. It doesn't play nice with quantum field theories either. We can play around with quantum fields in curved space-time, but as soon as you have the quantum field interact with the curvature of space-time, basically the math just messes up. But one approach people took was maybe there are extra dimensions. So it turns out that some of these problems seem to go away if you assume maybe the 10, the extra dimensions are rolled up. So you have the superstring theorist having elementary particles being rolled up in a very small scale. Uh, and it turns out that in this case, if you have these extra dimensions, you can gravity on small scale like it does on large distance scales. Gravity. And this is a reason why some physicists thought that maybe we are going to see small black holes forming when we actually hit elementary particles with sufficient energy. Because normally you would need to have enough energy in a small space that you actually get enough curvature of space-time to get a black hole. And basically that's not going to happen at normal particle accelerator because it's a ridiculously high energy. But if gravity gets stronger when you have a very small size scale, maybe you could get mini black holes. Then everybody expected that they would decay immediately into Hawking radiation. So it would just look like any other collision in the accelerator, except that you would get a really weird pattern of new particles. So that's something some physicists were really hoping to see, because that would be awesome. And then, of course, some others got a bit worried. Wait a minute, getting black holes into our particle accelerator, couldn't that be dangerous? And at this point, you got this interesting dynamics where many members of the public were feeling a bit queasy about this. And they didn't get reassured when the physicists told them, no, it's totally safe. Because when you think about it, how do we know it's totally safe? You're basing that claim on Hawking radiation that we have never ever seen. It's just theory. Yeah, all of this argument is totally theoretical, but we might be wrong about our theory. That's actually why we're building big particle accelerators. So that led to this debate about maybe it's dangerous to turn on particle accelerators. And after a while, enough people got concerned and started complaining that the physicists were actually forced to come up with good arguments why they were safe. And it was not just black holes that could be a problem. Another possibility that's allowed by our understanding of a standard model is strange matter. So this is like normal nuclear matter. Protons and neutrons bound together by the strong nuclear force. But instead of just being up and down quarks, you also get strange quarks. And it's assumed that under some conditions, it might be more stable than normal matter. It would be super dense. It would be as dense as a neutron star. So if you got a little nugget of it, if it had the right properties, it would gulf up normal matter and turn it into more strange matter. If something like that could show up, then we might be in trouble, because it might be eating Earth. It might be gobbling up matter, growing bigger, gobbling up even more matter. And before we know it, Earth implodes into a small nugget of strange matter. Entirely theoretically possible, except of course that we have never ever seen something like that. So there was a whole bunch of scenarios like this coming from physics that actually looked like this could be pretty dangerous if they could actually happen. So at this point, some people are saying should not turn on that accelerator at all. It sounds dangerous. The physicists now had to explain why it wasn't dangerous, and there is a very good argument, and that is that cosmic rays have been hitting Earth since the beginning, and many of them have way more energy than you could ever get in a particle accelerator. Indeed, it turns out that there is a famous instance, the oh my god particle, that had about as much kinetic energy as a baseball. And this was probably a single proton. This kind of super energetic particles hit Earth about once a year per square kilometer. Not that often, but if you could make a black hole or a strangelet or cause vacuum decay or any of the other disaster scenarios, they ought to have happened by now. So to most people, this is a totally reassuring argument, and we should just turn on the accelerator and try to do some science. However, some skeptics got a bit worried. Wait a minute, if Earth had already turned into a strange matter nugget, we wouldn't be around. Maybe we have just been on a very lucky planet. Fortunately, you can make an argument that, well, the moon could have been turned into a nugget and we would still be around. We don't notice any nuggets around in the solar system. So this doesn't seem to happen that often. It turns out that you can quibble with the argument in a lot of ways, and you need to patch it a fair number of steps, but it does hold up. But you need to do a fair bit of legwork. It's not as easy as just hand waving away the risk. And given that's about the survival of the planet, one shouldn't. One should take the concern totally seriously and analyze it carefully. Anyway, my friend, he had read the paper I wrote about this, where I pointed out that given that our theories are very uncertain about this, you probably don't want a single good argument against it. You want about half a dozen that overlap. So if one of the arguments is wrong, it doesn't matter because you have several others. And he noted that most of his arguments hinge on the fact that if you get this kind of weird disaster, you're going to see a big explosion in the sky somewhere. Many of them are basically observing the universe, and we look at the number of supernovas we see and notice that it's not that many. If the universe was a really dangerous place, we would see stuff blowing up in the far distance at a fairly brisk rate. But what if instead of stuff blowing up, it just gently and quietly faded away? So in his scenario, there is a weird interaction that produces something that catalyzes the conversion of normal matter into dark matter. So instead of Earth turning into a dense little quark nugget, it instead turns into this wispy cloud of dark matter. So this scenario, he called it the dark fire scenario, which sounds really awesome. It's really weird, and it's kind of an interesting thing to work out. Okay, why can't this happen?
I'm here, I'm listening. Yeah, so one thing I wanted to mention about strange matter is if you see a neutron star, you said strange matter is as dense as neutron star matter. So how would you know if a neutron star actually is a neutron star and not a strange star?
Yeah, that is something astronomers are discussing a lot because, of course, it's hard enough to even see a neutron star. A typical neutron star is about 10 to 13 kilometers across. That's not much. So we have telescopes good enough these days to see the surface of certain giant stars. So observing the neutron star, you can only look at the spectrum from it. But sometimes you can also get other information like radio emissions from pulsars, which are neutron stars where strong magnetic fields and hotspots generate radio signals. There was a recent paper that actually used some very clever statistics to figure out where on the surface of the star the hotspots were located and could make a kind of map. It's not a very interesting map because it's basically a map of two spots, but we roughly know where the spots are on that particular star. And you can use these kind of signals to figure out how large they are. If we're orbiting around another star, we can look at the orbit and figure out the mass. And that allows to figure out some interesting things. Another thing is to look at glitches. Some pulsars occasionally change frequency because they have star quakes. They literally compress a little bit. It's a bit like when you're squeezing a snowball, and sometimes it kind of gives way a little bit more to become a bit denser ice. So these things allow you to make some models of neutron stars. So the outermost part of a neutron star is kind of normal matter, except that it's probably an atmosphere of gaseous iron. And then you have a crust containing very weird isotopes. And as you get deeper and deeper, you get atomic nuclei pressed together until they start merging. There is something called the antipasta sequence. It's believed that at first you get small nuggets of neutrons embedded among all the other nuclei. So this is called the fricadelle phase because of an analogy with Italian food. And deeper, they start linking up into long spaghetti-like structures. That's the spaghetti phase. And then you might get the lasagna phase where they're forming these plates. And then you get to the anti-spaghetti phase where you have nuclei forming long spaghetti, followed by the anti-fricadelle phase where you have nuclei embedded in neutronium. And then you have pure neutronium, which is actually a mixture to some extent with protons and electrons and a bit of it. But as you go deeper, the density increases, the pressure is higher. And at this point, you might get quark matter or strange matter or other weird things. Physicists and astronomers have been having great fun coming up with all sorts of extremely exotic constituents. Now, the interesting part is if you have an equation of state, you can make models of how a star would behave. An equation of state is basically the relationship between pressure, density, and sometimes temperature. So the most well-known one that people encounter is probably the ideal gas equation. that tells you that the pressure times volume equals the temperature times some constant that depend on what gas it is and some other properties. So if you increase the pressure while keeping the volume constant, the temperature will tend to go up. If you heat it up but keep the volume constant, the pressure will go up as well. Other materials have other equations of state, and there is a lot of debate about what the true equation of state of a neutron star is. Now, you can make some good guesses here based on the size, how they respond to star quakes, etc. But it's still a lot of uncertainty. So people have been observing a lot of neutron stars and trying to see which equations of state fit. And of course, some of them correspond to very exotic kinds of matter. So the current effort is to try to understand what is going on with the really heavy neutron stars, because they don't really fit many models that well. So if we could find some good data on them, then we might know that they contain quark matter at the core. None of the neutron stars we've seen so far seems to be a really strange star. And if strange matter was actually dangerous, you could actually get a star that's 100% strange all the way up to the surface. If it's just hiding in the core of a very dense star, then it's probably not that dangerous. So the fact that we haven't seen any strange stars is kind of a good news for our general safety.
Yes, well, neutron stars are dangerous in and of themselves. I think I was reading somewhere that the surface temperature is 1,000,000 degrees or something. That's like that would vaporize you instantly.
Well, there is a weird problem here. It's really hot, but it's also really small. So it actually has a hard time releasing all that heat energy. Obviously, it's emitting a lot of X-rays and gamma rays and other stuff. So if you're too close, you're going to get fried by the radiation, even if the heat is not getting you. But still, the total amount of energy you get rid of it grows with a fourth power of temperature. So 1,000,000 degrees is going to give you a very effective radiation, but it also grows with the surface area. And the surface area of a neutron star is not terribly big. The sun has literally millions of times the surface area. And even though the temperature is lower, it can actually release way more energy. So when a neutron star forms, it actually has a problem. How do they cool down? And it's a very cool process actually called the Urca process that does that. Have you heard about it?
No, I just know that it emits neutrinos when they're first formed. But what is that process called? I mean,
Yeah.
it's
So,
called
so
about.
that neutrino cooling process is called the Urca process. And I've seen physics papers writing it in all caps as if it's an abbreviation for something. But that's actually totally wrong. It's actually a name of a casino in Rio de Janeiro. Or actually, it used to be because I think it's kind of has closed in the intermediate years. What happened was back in the day, George Gamov and Mario Sandberg were visiting Casino da Urca, and they were spending money and losing a lot of money at the roulette table while talking about neutron stars. And then they came up with this explanation of what was going on and realized, whoa, this could actually get rid of energy from neutron star as fast as our money is disappearing here in the casino. So that's the reason why it's called the Urca process. And it's a fairly simple one. So if you have in the normal neutron decay, a neutron decays to a proton plus an electron plus an antineutrino. Now, if that happens, of course, that neutrino could go off on its merry way. Now, a proton, on the other hand, can gobble up an electron and turn into a neutron, emitting a neutrino. Now, in normal matter, this doesn't happen very much. But in the core of a very, very hot young neutron star, this happens all the time. And a lot of neutrinos and antineutrinos are just shooting out and getting out of the star. So the normal photons that would transmit the energy in a star like the sun, they don't have a chance of getting out. And the surface is so small that the lucky ones on the surface, they don't amount to much. But the neutrinos, they can actually get rid of an enormous amount of heat. So the end result is that this cools down the neutron star in the early days, literally the first day or so, or even the first few minutes. from a billion degrees down to a mere million degrees, then it kind of shuts down because it's not enough energy. And at that point, it cools down much more slowly.
Oh yeah, that's actually pretty cool.
Yeah, it's amazing. And a neutrino cooling, in some sense, it would be the best cooling ever, because when you want to cool an object, you want the surroundings that are much, much colder and have less energy than you're radiating. So the neutrino background, there is very little energy there. So if I could just emit my waste heat as neutrinos, everything would be really fine. The problem is, of course, emitting waste heat as neutrinos requires some kind of nuclear interaction involving the weak nuclear force, which doesn't interact that much. It's kind of lazy force compared to electromagnetism and the strong force. So the end result is that it's very hard to actually emit with neutrinos. So we can't really cool that well using neutrinos. So we instead tend to use things like heat fins that are metal, where you put a lot of heat so the electrons wiggle around and produce electromagnetic disturbances, that is photons, that then go off, and then we can cool things down to the background temperature of the universe, 2.7 Kelvin, which by human standards is cold, but still it's kind of nearly 100th of the temperature we're at right now.
Yeah. Also, another thing I'm curious about neutrinos is why are physicists why do they think that it's their own antiparticle? That neutrinos could be their own antiparticle? Is it because they don't interact via the electromagnetic force, thus they don't carry electric charge? I don't even think they interact with the strong force either.
Yeah, so neutrinos, they're neutral, as the name says. So they don't interact at all with the electromagnetic field. They have some mass energy, so they do have a little bit of a gravitational interaction. They definitely don't seem to interact with the strong nuclear force, so that kind of leaves them to interact with stuff using the weak nuclear force. And given its weakness, that means that you don't get that much interaction. Now, the tricky question is, are neutrinos their own antiparticles or not? Nobody has so far seen a neutrino-antineutrino collision. Um, and there are some particles like photons that are their own antiparticles. And there are some quarks that have a different antiparticle. And this, of course, has very important issues for the kind of field theory you build to describe what's going on. Um, because this has to do with the symmetries of the forces and the quantum field. Now, I'm not great at neutrino physics. I honestly don't understand at all what's going on there. Um, and I don't think that many people really believe that neutrinos and antineutrinos are the kind of the same thing, because it also has a lot to do with the handedness. One of the big surprises is that parity is broken. That is, mirror symmetry is not behaving as you would expect. So you could imagine doing a physics experiment and watching it in a mirror. Would that also show up as a reasonable physics experiment? It turns out that actually there are some interactions where if you look at them in the mirror, you can say, that's a mirror image. That's actually not a real experiment. And this involves these problems of, it's called parity charge conjugation and time reversal symmetry. So normally, if you flip time, you turn the particles into antiparticles by flipping the sign. Most physics seems to behave very nicely there, except the weak force. You don't get the right interaction. You also need to do a mirror image trick here. I have no good sense of why and how this makes sense at all. This is beyond me. But this means that you have interesting things like the handedness, the spin of a neutrino. It has a spin, it's a fermion particle, can be aligned with its direction of motion or opposite. And it seems like you only get left-handed neutrinos and right-handed antineutrinos, or maybe it was the reverse. I can never remember this. I'm having trouble enough with my shoes, as the case might be. So if they were the same thing, then presumably there would be some more aspect of a symmetry here. As I said, I'm not very good at this. You should probably ask a real neutrino physicist about it. But if we were to find out that they were their own antiparticle, that would tell us a lot of important things. So this is another good reason to do a lot of particle physics. And you can do that, of course, not just in the form of a particle accelerator, but just by looking at cosmic rays themselves. So I have a friend who actually is a real neutrino physicist who's been working at the Japanese Super Kamiokande detector. So they have this enormous tank with distilled water, with detectors around, and then occasional neutrino passing through interacts with one of the atoms and produces a little light show, and they can detect where it was coming from and how much energy it has. And indeed, they've been able to image the sun through the Earth. They can literally see that the neutrinos are coming from the sun, and most of them go straight through the Earth, but a few of them get caught by the detector. Famously, in 1987, the neutrino detectors actually saw the supernova in the Large Magellanic Cloud. Again, yeah, I think it was something like 20 or 30 neutrino captured in instruments across the world, but they all arrived at the same time and kind of pinpointed that. So this kind of experiments can also be very valuable, especially since some of these particles can have energies way beyond what we can make in particle accelerators. There was some recent results showing that the ultra high energy particles, the oh my god particles, it looks like they're coming from generally directions where there are a lot of galaxies. Whatever is generating them seems to be following the cosmic web where you have galaxies and presumably black holes, supernovas, and other energetic processes that somehow make these particles and somehow accelerate them to super high velocities. And then they move along the magnetic field lines and occasionally hit the Earth and very occasionally hit a scientific instrument so we can detect where it was coming from. And of course, if you could just carefully gather the fragments when they hit something, we could probably find out quite a lot of cool physics.
Yeah, yeah, that's a lot of cool physics. And speaking of black holes, this will be one of my last questions. What forms the ones at the center of galaxies? Because they have way more mass than a star or any star. Because I know there's an upper limit on the mass of stars. So supermassive black holes have millions to billions the mass of the sun. That's still nowhere near the overall mass of the galaxy, but that's still pretty huge. Do physicists know where they come from? And why are they at the center of a galaxy? Why is that so special?
So the reason they are at the center is actually fairly simple. Imagine that you have a black hole that gobbles up random things, but the random things are all orbiting in a galaxy. So you're essentially summing random directions together, and that eventually tends to sum towards zero. There is also something interesting that the more massive an object is, as it's moving through a cloud of other objects, it tends to be slowed down by it. You can imagine a gas of stars and then a heavy black hole flowing through it. The stars are going to be drawn towards it. Most stars will, of course, totally miss the black hole, but when you do the math, if you or simulate it on your computer, it's quite fun to do actually. You get a wake behind the black hole where you get more stars than in front. So overall, the black hole is always going to feel a pull towards the stars behind it. So it's going to slow down a bit. That genetic energy actually gets transmitted to the star. So the black hole, in some sense, makes the other stars move randomly a little bit faster. But this means that slowly black holes that are very massive spiral inwards and eventually end up at the core of a galaxy. Now, you could imagine that this is a good reason also why various black holes meet each other in the core of a galaxy. You have a lot of stars there that will, of course, burn out and turn into black holes. But you also get these inspiraling black holes from the outskirts getting close to each other and eventually merging. Now, there is a fair bit of debate about the details of this process. There is, for example, something called the last parsec problem, like the last mile problem, that once you have a few big black holes orbiting a few light years away from each other, at this point, there is not that much making a spiral inwards. They're already at the center, more or less. So what makes them take that final step and plunge in? And people are doing a lot of simulations for this. And it seems like people have some idea about how that can be resolved. There is also a debate, where do but these black holes come from the beginning? because it turns out that stars, they give you black holes of a mass of a few solar masses up to maybe 100 solar masses, because that's the heaviest star you can normally make. If you have much heavier gas clouds, generally they tend to fragment. And the stars that are super heavy also tend to blow up so much that they actually don't even form a black hole. There are some ideas that in the very early universe, you actually had gas clouds that were so heavy that they collapsed into a black hole without actually forming a proper star. This has a lot to do with how much metals there is in the gas. So astronomers regard everything that's not helium or hydrogen as a metal. And metals are basically atoms that have a lot of electrons. So they're good at interacting with the electromagnetic field. So when you heat up this kind of elements, they can radiate away energy efficiently, which means that if you have a gas cloud of pure hydrogen, it's not going to be that good at getting rid of energy. It's going to very slowly condense inward. But if you have a lot of metals, it can condense faster. And this affects what kind of stars you get. So this is also affecting whether you get a lot of heavy stars or a lot of light stars. So it might be that we have primordial black holes, maybe some formed just because of inhomogeneities in the Big Bang itself, or these big gas clouds. I think most people expect that it's kind of a hierarchical process instead. Big stars, they implode into black holes, they then gradually merge with other stars and spiral inwards and form the supermassive black holes. So the Milky Way has Sagittarius A star, which is a fairly light supermassive black hole. It's only 4 million solar masses. It's fairly wimpy as supermassive black holes go. The really heavy ones, they can reach billions of star masses. There are some interesting questions about how big they could actually become, and nobody really knows where the upper limit is, but there are some theoretical arguments that the super ultramassive black holes probably can't get above 1 trillion solar masses. That would be way heavier than our in the entire galaxy, and nobody has ever seen anything like that. But anyway, even a normal supermassive black hole is probably the result of a lot of things merging over billions of years. And of course, different galaxies merging too. The Milky Way has gobbled up a whole host of other smaller galaxies. You can kind of see streamers, if you're using the right databases and telescope, of stars that don't seem to be quite orbiting the same way as the rest of the Milky Way, but are probably remnants of smaller galaxies that got gobbled up by the Milky Way. Now, the Milky Way has been a fairly good neighbor, actually. We're still a nice spiral galaxy, even though it's slightly wobbly because of large small Magellanic clouds. The other elliptical galaxies have gobbled up a lot more galaxies, and they presumably also have acquired their supermassive black holes, which eventually merge at the core, producing some impressive gravitational waves, and then sitting there. Okay, so that was my brief overview of what I think I know about supermassive black holes.
It was great. It was great. It was great. I'm learning. Trust me.
Thanks.
Yeah.
Yeah,
Yeah.
I find it fun to try to explain it because the cool thing about astrophysics is that it's a kind of giant lab that allows us to test our theories. We can build models of what's going on. We can simulate it. We can look at the sky and try to see, do we see that kind of stuff? And sometimes we do, and sometimes we get shockingly different things on the sky that we tells us there are physical processes we don't know yet that we need to figure out.
Oh yeah. Yeah. A lot. All right. I'm gonna have to go soon, but for the next meeting, I wanted to ask you just a few questions to kind of switch topics here in neuroscience. What are some
Cool. Yeah.
mysteries in neuroscience that you would want to figure out? They're probably, I don't know. I don't know how many there are,
Oh, yeah.
but is one like language or memory or what? Or the
So I
nature of
did my
sleep?
PhD on memory and trying to understand how do we actually store and learn information. And there are some weird mysteries going on there. And memory is one of the parts of the brain we actually understand fairly well. There are some fancy problems like consciousness that I have no clue on even how to pursue. And then there are important things like, okay, how do we actually prevent the brain from going bad because of Alzheimer's or damage? Or can we upgrade the brain? What about the different subsystems of brain? Can we handle them? For example, pain and suffering. How do they work? And can we avoid suffering without getting rid of pain? So there's quite a lot of cool stuff one can do with brains.
Oh, that's cool. Oh well, you probably know who he is. Do you remember Henry Meliasen?
Yeah, yeah.
Yeah. So what happened with him? They removed a part of his brain, and he couldn't form memories. Like what happened with him?
Yeah, so that's a classic case also in memory neuroscience. Practically every textbook brings up his case. So his problem was he had really bad temporal lobe epilepsy. So the brain works by having excitatory neurons that send signals to each other to send other signals. And if it was just excitation, everything would just be a feedback loop and nothing will work. So you have inhibitory neurons that tell the other neurons to shut up and regulate things. And this balance is super important. The problem is, of course, that balance can get broken, especially when there's particular kinds of brain damage. And this is why you can get an epileptic focus. That is a small part of the brain that just gets overexcited and causes the rest of the brain to go into a feedback loop to get an epileptic seizure. Now, the temporal lobe is interesting because in that part, there is an old part of the cerebral cortex, the hippocampus. It literally means seahorse because if you cut across it, it looks like a seahorse tail. And this is a region that unfortunately has a tendency to get epileptic seizures a bit more easily than other parts of the brain. Now, in this particular patient's case, the problem was he had really bad epilepsy, and this was back in the 50s, I seem to remember. So they just cut out the part of the brain that was causing it. It was so bad that it probably was necessary. But then, to their great surprise, noticed that he also lost his ability to form new memories. Now, before that, nobody had any idea where in the brain memory was. Indeed, there was a bunch of very classic experiments by Lashley in the early part of the 1900s, where he was trying to destroy part of the cortex of rat brains to see where is memory stored. And he concluded that it seems to be stored a bit everywhere. Then his findings were misrepresented by some journalists as we only use 10% of our brains. So that's actually the source of that kind of old claim. But it turns out that, well, we store memories across the brain, but in order to put them there, we need to use the temporal lobe and in particular the hippocampus. So it turns out that HM, as it became known in the medical literature, because you only use the initials to kind of keep people's privacy, he was the classic demonstration that, oh, the hippocampus is really necessary. So there was a few other cases like him, and then neurosurgeons got very careful about when removing an epileptic tissue from the temporal lobe. Let's not touch the hippocampus. You need to be super careful because that can really mess up somebody. Now, the interesting part is the hippocampus seems to be involved in doing memory consolidation. So during the day, you learn various things, but they're not really learned into long-term memory. It seems like they're stored in some intermediate form using the hippocampus and related systems in what's called the medial temporal lobe. It's on the inside of this lobe on the side of the brain. Now, during sleep, they seem to be doing replays of what happened during the day. Probably not during the dream sleep, but during the deep sleep. If you wake somebody up in the deep sleep state and ask them what's going on, they usually give a slightly garbled recount of something boring that happened during the day. It's not the exciting, weird stuff we're getting when we're having our dreams. It seems like what's happening is that the hippocampus replays important memories so the rest of the brain can learn them and store them in a distributed fashion. So in lab rats, for example, if you have them run around in a labyrinth, you have place cells in the hippocampus that get activated when you're in particular places. One cell might be activated by a particular corner, another one gets activated by a particular junction. And when the rats are sleeping after running through the maze, you can see them the cells turning on in the same sequence as they were running in the maze. And this seems to be involved in storing it permanently. So once it's stored permanently, you remember that even if your hippocampus breaks. And this is why Alzheimer patients, where hippocampus is one of the first parts of the brain to go, can quite often remember many things, but they forget what was going on just a short while ago. It's called anterograde amnesia. Kind of, it's forward directed. Gradually, of course, as the brain gets more and more disturbed, they also get retrograde amnesia. That is, they forget things that happened in the past. But many childhood memories are stored very, very securely. And that is usually the last thing to go. So that's kind of the potted history about how we found out the hard way that the medial temporal lobe and hippocampus in particular is really essential for learning and memory. And neuroscience has a lot of things to thank HM for.
Yeah. And his life was ruined, but he did help others understand the brain better.
Oh, yes. There is a very moving description of patients with slightly similar situations in Oliver Sacks' classic book, The Man Who Mistook His Wife for a Hat, uh, which is a very, very good book. But he describes two people, one that had this kind of damage to the hippocampus, and his life was ruined, yet he also was a person. The other person, he had something called Korsakoff syndrome. And this happens when another part of the medial temporal lobe memory system breaks down for other reasons. And he was equally unable to form new memories, but he was just constantly making up explanation was what's happening. So in some sense, he was not there. He was taking different roles. And Oliver Sacks said, yeah, the first patient, he got a soul. It's a person there, although he lacks memory and is confused about a lot of it. The other person is just cheerfully making stuff up. It's almost as if there was nobody there. It's a very disturbing thought, but even when brains don't work, they can fail in ways that are very differently affecting the whole being. There are some people with dementia where personality changes and they lose themselves, they become somebody else. And there are other people who are totally lovely people, it's just that they have forgotten everything.
All right. This will be my last question. This is non science. Would you rather, this is going to be a tough question. Would you rather lose all of your old memories, or would you rather keep your old memories but be unable to form new ones?
I think actually losing all my old ones, that's okay. Yeah, it's possible to relearn things. Of course, as somebody who's been looking into memory, I might also ask, what kind of memories? Because we have different memory systems. So the hippocampus and the medial temporal lobe are involved in what we call semantic and episodic memories. Semantic knowledge is things like Paris is the capital of France. And episodic knowledge is things like what I did last summer. Now, if you lose your semantic knowledge, you lose what you know about the world. That's pretty unlikely to happen because it's very widely distributed. Losing episodic knowledge seems to be easier because that seems to be stored in a few places. But there's also procedural memory, knowing how. I know how to walk. I know how to ride a bike. I know how to solve certain differential equations. I can't always explain how I'm doing any of these things. And it turns out that people with damage to the medial temporal lobe might have real trouble with the semantic and episodic memories, but their procedural memory is totally fine. There are also some conditions where procedural memory breaks down, but that's usually very bad news because we're kind of linked to our ability to function in the first place. But there are still some people who lose the ability to do certain things, even though they know how they're supposed to be doing it. So there are different parts of memory, which is very cool because once upon a time we just believed there was memory. And now we know there are different subsystems. We can even point at the different parts of the brain that do them. But getting back to the question, if I were to lose my memories of what I'd done, that's kind of sad, but I could still probably handle the world if I had my procedural memories. I would, to my great surprise, discover that I could ride a bike and solve a differential equation. On the other hand, losing the procedural skills, then I would be essentially a baby. That's not very fun.
Yeah, I would rather you keep your procedural skills but lose your other type of memories, because you could still live your life even if you lost your old memories.
Yeah, it's interesting that when you talk about somebody being a person, it's not just that they're conscious. It's something like to be that person. And they also have a particular styles of action. We would call that personality. Some people are more neurotic than others. Some people are very careful and conscientious, others are careless. Some people think it's very important that it's all about them, others don't care. And these things matter, of course, quite a lot. Even if you don't have memory, you can still tell people apart by how narcissistic or extrovert they are, even if they don't remember anything. And we also build and invent memories very quickly. Even people who actually have global amnesia and can't remember who they are, very quickly start telling a story about what they think they are. Because I think that's part of what kind of creatures we are. We're building narratives about our place in the world, where we have been, where we're going. And even if these narratives are totally made up stories, which is kind of true even for normal people, they're important for keeping us people.
Yes, I actually agree with you. I think you may disagree, but I think there's the mind, as in consciousness, and your memories, and then your personality, your predisposition, and then also your environment. So I think it's some combination of those four things. I
Yeah.
don't know how
And we
much
put
each weighs, but it's some combination of that.
Yeah, and we put quite a lot of our mind in our environment. The messy desk is not just a sign of maybe a messy mind, but also part of the mind is going on the desk as it's sitting there.
Yep. Oh man, this was actually pretty fun. I
Yeah,
always
yeah,
have
we can
class
totally
around this
keep
time.
doing an entire program just about different parts of the brain and the weird things that happen when they work well, or when they fail, or when you poke at them in different ways.
Yeah, yeah. I have to go, but
Yep. Well, it's been great fun. Thank you so much.
you're welcome. See you later. Okay.
See you. Bye bye.